Alright, let's try to solve one of these Planck's equation worksheet problems. I'm just going to make one up, but essentially you're given a wavelength. So let's say we have a photon of light. Pew! Alright, the photon of light is red. So we've got a wavelength in the range of 620 to 750 nanometers. Let's just say it's right at the edge of what we can actually see. So let's say it's 750 nanometers. Because that's the wavelength, we need to convert that to frequency before we can calculate the energy of the photon according to Planck's equation. So I'm going to list the things that I'm given in the problem. Just like any other time that I've worked problems with you guys, this is the first step. So I got 750 nanometers. That's the wavelength. The speed of light is a constant, so we know that in a vacuum it travels at 3.0 times 10 to the 8th meters per second. And we know that the speed of light is equivalent to the wavelength times the frequency. Remember, there's two ways to write frequency. I generally use the goofy looking F. So that's our equation. We're going to rewrite this, though, to solve for frequency this time. So we know that frequency has to be equal to the speed of light divided by the wavelength. The key here is to make sure that we've got everything in correct units. So we need 750 nanometers to be into meters, like our speed of light. The easiest way to do that is look at the prefix nano as meaning 10 to the negative ninth. So if you go back to the sheet that I gave you at the beginning of the year, you'll see that 750 times 10 to the negative ninth meters is the same thing as 750 nanometers. So I'm going to go ahead and plug some things in here. We got 3.0 times 10 to the 8th meters per second for the speed of light, divided by the wavelength, converted into meters. So 750 times 10 to the negative ninth meters. The only thing left to do now is solve. So I'm going to try to figure out how to move the screen here. There we go. So we're going to go up this way. One suggestion I have for you guys is go ahead and solve for the exponents first. So focus on these guys before you try to use the coefficients, these guys here. So I'm going to take 10 to the 8th and I'm going to subtract the exponents this time because I'm dividing. So I've got really 8 minus a negative 9. So essentially I'm saying that I've got 8 plus, right? Plus for our math gurus. So we've got 8 plus 9, so that'd be 17. So I know that my frequency value is going to end up being 10 to the 17th. However, I still need to take 3 divided by 750. So I'm going to take 3 divided by 750 on my calculator out here. And I get 0.004. My units, meters cancel out. I'm left with per second. And remember, per second just means hertz. So we're talking about a frequency that looks like it makes sense. I need to make sure that I take this value and put it into the correct notation. So I'm going to put it in scientific notation. I'm going to move the decimal 3 places to the right. By doing that, I have to change my exponent. I have to drop it down. So it would really be 4.0 times 10 to the 14th hertz, or per second. Not quite finished yet because we wanted to calculate the energy of the photon. So now I know its frequency is 4.0 times 10 to the 14th. I know Planck's constant because by definition it's a constant, it doesn't change. So it'll be 6.63 times 10 to the negative 34th joule seconds. So that allows us to calculate the energy of that photon of light. Remember, high frequency, high energy, that's the direct relationship between those two variables. So Planck's constant allows us to calculate the energy of a photon being equal to Planck's constant multiplied by a frequency. We drop up a little bit again. Oh, I messed things up big time this time. You just got to follow along with me as best you can here, because I'm not going to stop now and redo it. So I've got the H value, which is 6.63 times 10 to the negative 34th joule seconds. I'm going to multiply that by my frequency of 4.0 times 10 to the 14th per second. As you can see right away, the unit seconds are going to actually cancel out. I'm left with joule. Joule is what I want because I'm trying to describe energy. So that all kind of computes, made sure that my equation was set up correctly. Now I'm going to do the same thing I did before. I'm going to focus on those exponents first. So I'm going to take negative 34 and I'm going to add that to 14. So I know that my exponent is going to be to the negative 20th. Okay, so I'm adding 14 to negative 34. Next, I'm going to look at the coefficients. So 6.63 I'm going to multiply that by 4. I know my answer better be pretty close to 24. It ends up being 26.52. So my answer is 26.52 times 10 to the negative 20th. That's joules because my units worked out that way. But it's not quite finished because you know me, I really love sig figs. So to see the sig figs, we have to move the decimal place. First of all, to put it in scientific notation, so move the decimal place one place to the left. By doing that, I have to make the number bigger, actually, than what it is now. So the exponent's going to go a little less negative to 10 to the negative 19th. But as far as the coefficient goes, we need to round to the nearest tenth here. We've got 2 sig figs, so it'll be 2.7 times 10 to the negative 19th joules. So anytime you have to calculate the energy of a photon, if it's giving you the wavelength, you've got to convert to frequency first. Once you get that finished, you can calculate using Planck's equation. Good luck.